Okay, so now I'm going to show you an example that, another example on this subgroup. This is an example on AIDS. So in this example, we have 1,000-odd patients who randomized to a AIDS clinical trial. The data is from this book called Applied Survival Analysis by Hossman and Lemichaud. And so the treatment is either a 3-drug regime with a certain thing called IDV, or 2-drug regime without IDV. So AIDS drugs are, they call it cocktails. So they put a few things together, and then that becomes a drug. So we're comparing here in this trial a cocktail of 2 components versus a cocktail of 3 components. The difference is that component is something that maybe is experimental. It's called IDV. And so the idea is, does IDV help to improve survival for AIDS patients? Right? So the subjects, they're all HIV infected, and they all have very low CD4 cell counts. So CD4 cell counts are white blood cell counts, and the amount in your blood is a measure of how your immune system works. Okay, the lower it is, that means the less your immune system is working, and that's how AIDS people die, because their body cannot fight the AIDS disease. So all these patients have less than 200 CD4 cell counts at baseline, and they all had some prior therapy. So they all have at least 3 months of something called ZDV therapy. So I assume it's some sort of standard treatment already. And they were randomized, but stratified by CD4 cell count. So they want to make sure that everything is balanced. And so they took all those with low CD4 cell counts, and I think the randomization is maybe, I think it's 50. No, not 50. At time of screening. Well, they all have, yeah, I think it's 50. So they take a group of HIV patients who had lower than 50 CD4 cell counts, and then they randomize the 2 treatments within them. And the other group that had higher than 50, they randomized within that, right? So the doctors, somehow they think that that's important to do, so they stratified that. And the outcome was a time to an AIDS-defining event or death. So the response is how long it takes for them to show AIDS symptoms or for them to die, right? And but this trial was stopped early because apparently they found that it was the treatment was effective, so it was terminated early. And this example, there are no missing data. Okay. So what are the covariates? Well, first of all, the response is time to AIDS diagnosis or death. That's time. Censoring is the whether the event happened. The event is the event of death or the event that this person had AIDS. Right. So these patients did not have AIDS before. They're HIV positive. So their bodies show that they're infected, but they haven't gotten AIDS. AIDS is another diagnosis. Right. So there's this censoring indicator, which is a 1. If during the time of the trial, the subject had AIDS or died, otherwise it's 0. TX is treatment. TX is 1 or 0. So 1 means that the subject had this 3-drug regime with IDV. 0 means that it's without IDV. Right? And so the stratification variable is if a CD4 cell count at screening is less than 50. Right? So that's a stratifying variable. The age of the patient, the subject, the race of the subject, there are 6 categories. Whether the subject had used intravenous drugs before. 1 is never, 2 is currently, 3 is previously. So I guess it's safer to treat this as a categorical variable rather than an ordered variable. If you treat it as an ordered variable and you do sort of Cox proportional hazards model, it's not clear that they should be equally spaced, right? I think you have to think if you want to use IV drug as a linear predictor, you first of all decide whether you want to record them from 1, 2, or 3. And even you have to decide whether 2 makes sense to be in between 1 and 3, right? Otherwise, so it's more difficult. A safer way is to treat as a categorical variable with 2 degrees of freedom. Hemophiliac is 1 or 0, or 1 or 2. Hemophiliac is a person who's, once he gets a bruise, he will bleed, take a longer time for the blood to clot. And AIDS patients have these kind of problems. Karnofsky Performance Scale is a measure of how well the person is physical fitness. If a person has all of us here probably have 100, we're normal, with no complaints, no evidence of disease. You will have a score of 90 if normal activity is possible, but there are minor signs or symptoms of disease. 80 if you're normal with some effort, some signs or symptoms of disease. So maybe somebody has to help you walk up the stairs. 70 is you can still care for yourself, but work is not possible. 0 means you're dead. Okay, so there's a standard thing called Karnofsky scale. CD4 is the baseline CD4 cell count upon entry. This is prior treatment with ZDV, another drug, because you have to account for that, right? I mean, if you have patients that have where was that prior? Yeah. Oh, they all have at least 3 months of prior therapy. So now, how many months of prior therapy, right? So they were on, how many months were they given another drug? Okay, and that may affect the performance of this drug, right? And the age of the subject at enrollment. So as usual, the first thing you do is you fit a Cox proportional hazards model. In this case, you have no problem because no missing data. And what do you find? You find that treatment is significant, and that's why the trial was terminated early. So a trial is terminated early. If they find that this treatment is useful, then there's no point keeping those people on the other drug if you have actually found a useful drug. Karnofsky score is significant. Well, of course, because Karnofsky score must be predictive, right? If you're healthy, you're likely to live longer than if you're sick. So this is not a predictive variable, it's a prognostic variable. You can sort of guess that this must be significant. Your health at the time of coming to trial should be a good predictor of outcome, right? So this is not surprising. CD4 is significant, still significant, even though we stratified on CD4 cell counts, right? There's a stratum variable, and this is not significant, okay? But given what we have already talked about previously about interpreting coefficients, you should not be surprised, okay? So this is significant. So basically, STRAT2 is a discretized version of CD4 because whatever CD4 is, if CD4 is less than 50, STRAT2 is 0. If CD4 is bigger than 50, STRAT2 is 1, right? So STRAT2, that stratification variable, is a very crude way to just binarize this variable. Prior treatment is not significant. Age is significant, right? Barely significant, right? So this tells you that it looks like this treatment is significant, right? It's useful. But it doesn't tell you, are there people who don't benefit from this treatment? In fact, this doesn't really, it doesn't tell you, you look at this, you think that everybody will benefit, okay? Well, you fit a Cox model, you find that's not true, okay? It's based on CD4. If CD4 is less than 85, then you're in here, and then the blue treatment is much better than the red one. The red one is without IDV. If CD4 is above 85, then there's no difference. Okay? If it's above 85, the survival curves are higher. So if the CD4 cell count is above 85, these people are not in too bad a shape. They're all in bad shape, but at least relatively not too bad. the people who are really in bad shape are the people here, right? And here, that's where the drug helps. But what is interesting is that the doctors thought that 50 is a cutoff. They stratified on 50. Okay? But the data shows that maybe the cutoff should be 85. Right? So the data sort of supports the doctor's expectation. They just chose 50 because it's a round number. Right? They probably either 50 or 100, or 75. Right? So here's an example, sort of similar to the breast cancer example, where you find that overall there is a positive effect, but there are still people who don't benefit. So maybe these people, which is about 40% of the sample, should be, maybe there's no need to add that third component in the drug. Right? The two-drug regime is probably as good as the three-drug regime, right? Especially if the three-drug regime is more expensive. Okay. All right. So that's okay. Now I show you an example that no method can analyze, except guide. So here's an example on a gene study. This is from a drug company, and I'm not told what is the disease. I don't know. I was just told that they collected this data, 1,500 subjects, randomized to treatment or placebo. I don't know what is the disease. I don't know what is the treatment. And the response is survival time in days, 63% censored. 23 of them, there are 23 baseline variables, 17 ordinal, 6 categorical, and 282 genetic variables. Okay? But 95% of the subjects have missing values. So you look at the data matrix, 95% of the rows have missing values. And there are only 7 columns that are complete. So I'm told that this data set was sitting on a shelf in the company for quite a while. The trial was completed. You couldn't analyze anything because of the missing data. You can't even fit a Cox proportional hazards model using a complete subset because then you have too many variables. You don't have enough samples, right? 5% of 1,500, right? It's a very small sample size. But we have almost 300 variables. Okay? So, but if you look at the Kaplan-Meier curve, it seems that treatment is better, right? But it may be that this treatment difference effect is not enough to get the drug approved. Okay? So it may be interesting to see if you can find a subgroup where the treatment effect is bigger. And you run guide, and you get this tree. And now, in fact, in this group, it is, in fact, a bigger effect, and here you have no effect. So this is usually what happens, right? You do a clinical trial, you get a certain effect. That's an average effect, right? There must be some people who benefit more and some people who benefit less. Okay? If that average effect is good enough to get the drug approved, then, of course, you just get the drug approved because then you sell to more patients. Right? But if it's the average effect is not big enough, and you still want to salvage something, right? So maybe you can try this. Not that with this you can go and sell the drug. No, the FDA will still want you to do another clinical trial focusing on this group, right? And prove that if you only collect patients with this characteristic, that indeed you can replicate this, right? But at least you get some clue to follow up. Otherwise, you don't know what to do. Okay? So this says A2. A2 is a baseline variable. I don't know what it is. It says that if it's less than or equal to 0.1, or if it's missing, then you go to here. There are 863 patients in here. The other group are people with A2 bigger than 0.1 and not missing, and they are here. Right? So it used to be that that's all I could do, and then when you show this to the doctors, they want to know whether this is statistically significant. And it used to be, I said, I think, I can't tell you. This is it's impossible to answer. And then, of course, they get disappointed. And I feel bad, too. But now I can tell you, I can give you 95% confidence intervals for the relative risk. So this is a confidence interval using a bootstrap, which I'll tell you shortly how I get it. The relative risk of treated versus untreated. So relative risk is 1 if treatment does not make any difference. Okay? If it's less than 1, then the risk is lower if you get treated compared to not treated. So you see this interval does not contain 1. And that's why this is the separation. This one contains 1. Okay? Contains 1, so it's not significant. All right. But before I tell you about those intervals, you can extend this, and I have extended this, to multiple responses. So far we're talking about one response survival time. But sometimes you have multiple responses, as the next example. Right? So here, where's my next example? Oh. Maybe I'll go to the multiple response first. Right? So here's an example. This is a diabetes trial. So these patients are randomized to 52 weeks of a treatment, drug A or drug B, and then they follow them up, every 6 weeks or so. Okay, so they first look at them 2 weeks before the start of the trial. Then they look at them, take measurements from them, beginning of the trial, 4 weeks later, 8 weeks later, 12 weeks later, and so forth. Right? So there are 10 time points. So your Y variable here is the A1C, blood sugar level. Right? So diabetes, can be so measured by how much blood sugar in your body. Right? So what I understand from diabetes is the following. It's really quite interesting. So our human body, all our cells, need 2 things to avoid dying. One is we need oxygen. Okay? The other one is our cells need food. Food in terms of blood sugar. Right? So if you stop giving your cells oxygen, they'll die. That's why even when we sleep, we breathe. Because if we sleep and we don't breathe, we never wake up. Our cells will all die. They need a constant supply of oxygen. Right? So nature made every animal breathe all the time, whether you're awake or not. But nature cannot make everybody eat all the time, even when you're sleeping. Because then you don't have time to do other things, right? And you'll be constantly eating. But the cells, your brain cells, all the cells, need constant supply of food. They don't care if you're sleeping or not. They still want food, or they die. So what does the body do? The body comes up with this mechanism that allows us at least not to have to eat all the time. So after you eat breakfast, okay, your food is converted to blood sugar. And then your body has a lot of blood sugar. It's in the blood, right? Then the body will secrete a hormone called insulin, right? This hormone is secreted, I think, from the pancreas. This insulin will turn the blood sugar into something that you can store in the muscles or in organs, like a reservoir. Okay? So after breakfast, if you're a normal person, this process, if it works well, then all the food you eat is stored. And then you can go and attend lectures, you go watch a movie until lunchtime. In between, another hormone will slowly release this from the muscles, turn it into blood sugar. So even while you're watching a movie or you take a morning nap, your body still gets food constant. Right? You have diabetes if this process doesn't work well. Okay. Either because you don't have enough insulin, your body doesn't produce enough insulin, so you have a lot of blood sugar in your body, but it doesn't get changed into food, stored. It's not stored. Right? If it's not stored, not only do you not have stored food, you have too much blood sugar that will destroy your organs. Okay, the blood sugar floating around, you cannot allow it to float around too long. Damage your organs. So you have to get rid of it. Okay? All right. So people with diabetes are people who somehow their body this process is not functioning well. So one type of diabetes patients are patients who don't produce enough insulin. Right? So sometimes you see people have insulin injections. Right? They take, artificial insulin. They inject. They produce insulin. Right? So one drug, say drug A, it will give you more insulin. I don't know whether it's an injection or it could be something that maybe just persuades the pancreas to pump out more, right? Sometimes your pancreas is lazy, doesn't want to put out more insulin. So you take a drug, and then the drug tells the pancreas, pump out more. So once you pump out more, okay, then you have insulin. So that's drug A. But there are other types of diabetes patients who actually have enough insulin, but somehow the body doesn't use it. So you have to wake up the body. You tell the body, hey, you have enough. Make it do the job. So there's a sensitizer. Okay? Make the body a bit more sensitive to the insulin. So you don't have to give it any more insulin. The body has enough. Just that the body is not using it. Right? So the purpose of this trial is to see whether drug B, for what kind of patients will drug B be better than drug A? All right? So what are the predictive variables, the baseline variables? So HDL, LDL, total cholesterol, triglycerides, fasting insulin, and all this, age, weight, BMI, and so forth. Okay? Some of them have some missing values, some of them have a lot of missing values. C-peptide is missing about 1/3 of the patients. Okay? So when I first looked at this, I was wondering why. You see, we have 1,200 subjects. Why almost 600, almost half, have missing C-peptide? And I was told that because this is a multi-center trial, okay, for some centers, the doctors were not told to do that test. It's a lab test, right? The doctors were not told to do the C-peptide test. So there were some people, the test was not done. But it's almost half of the data. What do you do with this now? You want to exclude C-peptide? If you exclude C-peptide, you can still have all the observations, but you throw out one variable. What happens if that variable is important? Even though it's missing 50%, but maybe it's very predictive, right? If you want to keep it, then you throw out the people without C-peptide. So you have a data matrix. One column is C-peptide. You can throw out one column, or you can throw out all the rows where this column is missing, right? You throw out the rows, your sample size goes down to 50%. The third option is impute C-peptide. Imputing C-peptide, does it make sense? You impute with what? The average C-peptide for the remaining 50% of people? You impute with a constant, right? You want to do something more sophisticated? Well, how? Right? You want to impute the C-peptide for all Indian patients with the Indian C-peptide mean, and all the Chinese patients with the Chinese C-peptide means, right? But maybe it has nothing to do with race. Maybe it's got to do with male or female. Now you impute with the male Indians. Male Indian means a female Indian with a female. Eventually your group becomes smaller and smaller. You have more and more groups. But how about old male Indians versus young male Indians? Well, what is old? What is young? Right? So imputation is it's a big mess. Okay, and then there's this funny thing here. HOMA. All these are HOMA variables. HOMA is a measure of beta cell function in the liver, I think. Okay, that has something to do with insulin. So they measure the liver, maybe the pancreas. Right? So there's some measure, and they're all missing at the same time. That's because I think this is a test that maybe it takes a blood sample, and then once you have a blood sample, they have all three readings, right? So if you take it, you have all three. You don't take it, you don't have all three. I think that's otherwise. How can you be all 62? Right? I think it's all 62, same 62 people. And again, are they randomly missing? Right? Okay. Anyway, this is a picture. Right? So these are not survival curves. In survival curves, we plot the probability of survival. This is actually over time. Right? There's no censoring here. Actual A1C, blood sugar level. I'm told that for a normal person who is not diabetic, the A1C should be below 5. Below 5. See, all these people start with 8.5. They're very diabetic. Okay? They're very serious. In fact, look at this. Even with the drug, they never come down to 5. In fact, after a while, the drug is not so effective anymore. Right? That's the other problem, right? Many drugs, initially, they have some effect. After a while. So both drugs have the same thing. But which is a better drug? The one that's lower is better because you want to bring it down to 5 normal, right? So the rate is better. The A drug is better. Right? So the question is, is there a subgroup where the B drug is better? Now, if you have a method that you cannot handle multiple response, then you have to choose one time point as your final outcome, right? You either choose 52 weeks, or you choose 24 weeks, or you choose every one of the 10, but then now you have 10 models. One model at 4 weeks, one model at, right? So one model where you only analyze 4-week response and see whether you have a subgroup. Then you have another model that analyzes 8-week response and see whether you're a subgroup. And now you have 10 models, and all the subgroups are maybe slightly different, right? So you want something that is together, okay? And this is the model, right? This model says, so this model analyzes all of them together. This model says if HOMA B is less than or equal to 23.9, you come in here, and of the 1,200 people, 200 of them are here. And this is what happens to them on average, right? So I plot the A1C levels for those people in this group who are given drug B, the blue line, and then the A1C levels average for this group of people who are given drug A. So you see that drug A is still lower than drug B, right? So it's same as this overall, everybody together, no subgroup, right? So within subgroup, the picture is still the same. Drug A beats drug B. Now over here, HOMA B is higher, and then the question is fasting blood glucose. Right? If it's low or it's high. If it's low, then drug A is still better than drug B, but the two curves are a bit lower than this, right? So fasting blood glucose is, I think, a measure of how much blood sugar is in your body when you do not eat. When you do not eat, right? So there's no surprising that this is lower, because these people can control their blood sugar a little bit better than those. Now, this is an interesting group that you might be interested in if you want to see whether you can market drug B. Right? Here, drug B beats drug A. Not all the time, but after halfway. Right? So these are the people, you can describe them, two conditions. The intersection of this condition bigger than 23.9, and this condition bigger than that, and that's it. All right? Okay. So again, this does not prove that this is the right subgroup, but this gives the drug company something to think about. Do they want to have a clinical trial? So they have to think, how much money do you think they can make out of drug B? Right? Do they think that drug B can make a lot of money for them? If they think so, then they can continue to study the drug by having a clinical trial. But given that overall drug B is losing, the clinical trial has to be focused on a subgroup where drug B can win, right? And so this is a potential group, right? But before you go ahead, you have to ask the doctors who know about diabetes, right? Who know a lot about diabetes, whether this makes sense or not. And from my colleagues in that drug company, they say the doctors say this makes a lot of sense, right? This makes sense. Biologically, medically, it makes sense. But it may not make sense for the other people in the business in terms of sales. So you look, we have 1,200 subjects, right? 1,200 subjects. Of the 1,200, only 163 are here. It's a bit over 10%. Right? So if you have a drug company, you calculate, there are only about 10%, 15% of people who might be given this drug. Right? Is that a big enough patient population to make money out of it? Right? If you think yes, then they would have to, do another clinical trial, independent, to prove that drug B is better for this group of people. And then at that point, they need something like this, because they don't know what is that group. Right? Now, well, do you believe these results? Over here, I put confidence intervals on them. You see those bars? Now I want you to imagine for a moment, without those confidence intervals. What is your impression? Look at these pictures. The same curves, but without confidence intervals. You would think that, oh yeah, the separation here is pretty big, right? You really need those confidence intervals to tell you how likely that this is due to chance. Right? So that's where you need those confidence intervals that give you some At least here you can see that over here they're quite significant. They don't overlap, right? But over here they start to overlap. Over here they overlap a lot, right? And here they almost overlap. Okay, so this is what I think we as statisticians, if you want to get into precision medicine, I think you need to not only find the subgroups, you have to have some standard errors, some confidence intervals, right? The question is, where do these confidence intervals come from? Okay. Okay, so this is a fundamental question. Okay. How do you do inference after subgroup selection? First of all, the subgroups are random, right? So you look at this one. Okay. We have a subgroup here. It says A1, A2 bigger than 0.1 is here, right? If you repeat this trial, you may not get A1 bigger than 0.1. You may get A1 bigger than 0.2. Or A1 bigger than 0.05. Or A2, I should say A2. Or you may get A1 instead of A2, right? Okay. And yet you want to estimate the effect of treatment in here, but this group cannot be replicated. You may never see it again. So how do you go about that, right? So like here, from here, we can calculate the difference and say, the relative risk. The relative risk is say maybe 0.6, right? 0.6 based on this data. If you calculate 0.6 based on this data, you are just using this data. You're ignoring the fact that you did a search, right? Right. I think it's maybe, if I forget about relative risk, a simpler case is when you just have Y and not censored. So suppose we have a tree like that, right? So it's node 1, node 2, node 3. Okay? So we have a treatment, Z equals to 0 or 1, right? So in here, we have N2 observations, and here we have N3 observations. Okay? And so we can calculate Y0 bar and Y1 bar. Y1 is this Z equals to 1, Y0. So we can calculate this here and say this is 2 and 3, right? And we can calculate the same thing here for this node. Equals 1.5 and 1.7, right? Okay. Right. So this is based on the data here. So the difference is Y1 bar minus Y0 bar, right? Which is 3 minus 2. This is 1, right? What you want to know is what is the standard error for this? What's the variance of that, right? The precision of that. If this standard error is 0.1, then you will say, oh, okay, I'm quite sure, right? The treatment is quite effective because my standard error is so small. But if this one is 0.9, now you're not so sure anymore, right? Right? The question is, where does this come from? This is standard error, right? This is standard error. Okay, of the difference. Right? So how do we calculate standard errors in practice? So in traditional statistics, you think they have a population, and then you have a mean mu, right? Then you collect data to estimate mu. So x1, x2, x3. Right? Okay, so then you use x bar to the mean, right, to estimate mu. Right? So you want to find out what is the standard error of x bar. This is square root of the variance of x bar. Right? Okay. How do you calculate that? Well, conceptually, this is what you do. You take repeated samples, right? So you repeat sampling, right? So you take one sample, x1, x2, xn, right? You calculate x bar, right? Then you do it again. Let's call this 1, x bar 2. And then x m bar, right? Okay. So every time you sample, you still have this picture. Right? So you take a sample, you get x1 bar here, right? You take another sample, x2 bar here, right? And so forth. Okay? And then from here you can draw a histogram, right? The sampling distribution of the means, and it's like that. Right? Because if this variance is sigma squared, this variance is sigma squared over n, right? This is variance of the mean. Right? Okay. So if you do this, you can just calculate the sigma hat squared over n to be summation xi bar minus, let me call it double bar, squared I equals to 1 to m minus 1, right? This is how you would empirically estimate the variance, if you can draw, right? But in our case, every time you draw, you get another tree. The mu changes, right? You see, in this tree says A2 bigger than 0.1 or 0.1, right? So this is your first draw, right? So the mu, the mean of this node, the mean for either treatment, it depends on this set. But now you take another sample, you do another clinical trial, you get another tree. Right? Now the mu for this set is not the same as the mu for this set, because this set is different from this set. Right? If you take another trial, it says B3 bigger than 0.1. Now it's B3, it's not A2. Okay? So what do you mean by the variance? What do you mean by variance? I think of it the following. So suppose you want to do oil exploration in the Gulf of Mexico, right? All the companies, they try to look for oil. So this is the Gulf of Mexico. So you are Exxon, right? So you are engineer Exxon. So you want to find out where you can drill for oil. And suppose this is one spot. This is one spot, right? So you have some fancy machinery. You can do sonar and so forth and figure out whether it's oil, right? So, and suppose your method is 95% accurate. 5% of the time you find the wrong place. This is like 95% confidence interval, right? So 95% of the time, it will identify this area. Okay? Right? How do you know your method is good 95% of the time? Because if you keep doing it, 95% of the time is going to be here, 5% of the time is going to be here. Right? 5% of the time is wrong. That circle is off. Right? So this is what we do traditionally. But in this case, it's not the same as all exploration. You're trying to catch a fish with a net. Every time you throw the net, the fish would have swum somewhere else. Because every time you take another sample, you get another subgroup. Right? You will get another subgroup. Right? So this is like different from all exploration. All exploration, that position is there. You don't know what it is, but it stays there. It doesn't move around. Okay? It's not that every time you guess, it's somewhere else. But spear fishing is different. Okay, spear fishing, unless you want to try to catch a dead fish, this fish is moving around, right? And yet you want to be 95% sure you can catch it, or you throw a net, right? So this fish is floating. Okay, so if you have a 95% procedure, that means 95% of the time you can catch this fish, no matter where it's swimming. Okay. So how do we do it in statistics here? So a confidence interval is like an interval. You capture the unknown, right? It's like a net. Okay? So that's my first point here, right? The subgroup is random, not only because the data are random, but the algorithm, the machine learning algorithm, will give you a random in the sense that it will change based on the data. The parameter you're trying to estimate will change, not the estimate will change. The estimate, of course, will change. X bar will, of course, change here every time, but the mu doesn't change, right? But in our case, the mu changes. The mu is the true mean of y0 and y1 in here. Right? There is some true mean, but you want to estimate more accurately by taking another sample? Well, that true mean changes because your subgroup changes. So that's why for almost 30 years, I thought this problem cannot be solved. You cannot even replicate. Right? When you talk about variance, it's long-run behavior, right? But you assume that things are replicable, but it's not replicable. So unlike classical theory, the true, I call it mu, but I call it theta here. The theta are also random. The theta here is defined by your sample, right? If I have a different sample, I have a different subgroup, there is still my expected y in there. But it's not the same expected y there as the expected y there. So now your theta is also random. Okay? So whatever you want to find out whether it's the difference here, 3 minus 1, whether it's statistically significant, right? You have to take into consideration the search there. You cannot do this. You see, if you don't care about that, you can get a t interval for this, right? This two sample problem, right? You have one set of data with placebo, one set. It's a two sample t-test, right? So you can construct a t interval if you ignore the fact that you had searched very hard for this. You can get the pool estimate of. So let's say the data here are y01, y02 up to y0 and 0, and then y11, y12, y1 and 1. Right? This is placebo. And this is drug, right? So this may be A1C levels, right? Just think of that one time point. So if you do that, if you have that, then you can assume that now you have two distributions. This is the placebo, and this is the drug, right? And then these are the drug observations here. And these are the placebo right? You do two-sample t-test, right? You estimate the variance for the placebo. You estimate the variance for the drug, right? So S0 squared is sample variance for placebo, and S1 squared is sample variance for drug, right? The usual formula for sample variance, just, find the mean, take the difference between each and the mean, square, sum divided by n0 minus 1, right? So this is summation y0 I minus y0 bar squared n0 minus 1. This is summation y1 I minus y1 bar, right? And then you can pull it. SP squared will be n1 n0 minus 1 s0 squared plus n1 minus 1 s1 squared divided by n0 plus n1 minus 2, right? Okay? And so you can now get say 95% T interval, right? Is y1 bar minus y0 bar plus and minus some T multiplier, right? Degrees of freedom nu is n1 plus n2 minus 2, right? That's the divisor here. So T alpha over 2 SP square root 1 over n0 plus 1. Right? That's your standard undergraduate formula for a T interval. Right? This alpha here is 0.025. Right? So this is a T curve. Right? And this is alpha over 2. And this is alpha over 2. Right? So this is T mu. Right? So it's about 1.96 or 2. Okay? But if you use this, you are pretending that this was given in advance. Actually, it's not given in advance. This came out from some search. Some machine learning algorithm that does a lot of search to get this. So this will be wrong. Right? In fact, you would think this interval is too short. You agree? Because SP is trying to estimate the variance of this, right? But the variance of this does not take into consideration the variance of choosing A2 and the variance of choosing 0.1. Right? This variance here is only based on the data at the end of the algorithm, right? It doesn't. There must be variance here because there must be uncertainty here, right? Even if you choose it correctly, A2, how do you know this 0.1 is the right place? Right? So that's a difficulty there. Other methods, they use permutation tests to try to solve this problem. So one thing they try to do is they try to take the data and then permute the treatment label. Okay? If you permute the treatment label, you can test whether the treatment has any effect. But that's globally, not locally. What we want is for this subgroup. Right? Okay. So that won't work. So in the end, okay, so what did I do? So here's, you can imagine the following. Right? So suppose I don't know what else to do. And I only know the T interval. So I only use this T interval. Okay? But I know this interval is too short. Right? So here's my T table. Right? So I have my alpha here. Alpha is 0.001, 0.002, up to 0.050. Okay? I start with 95, so I start with 0.025. This is half alpha. Right? So I read in there, I see it's 2.1 in my t table, suppose. Right? So now I put 2.1 here. Okay? This I can calculate. Formulas are there, right? So I have this interval. But I know it's too short. Okay? But I have a good friend. His name is spelled G-O-D. So this good friend knows a lot. So I asked this good friend, G-O-D, to do the following favor for me. I said, I want this interval to cover 95%, but I know it's too short. So I know it covers less than 95%. Can you tell me what does it really cover? How much does it really cover? I know it's not 95%. I know I'm kidding myself if I put 95% here. I know it's too short because I did not care about these things, right? So my friend has all the data. Suppose my friend owns a population. You see, if my friend owns a population, all I have to do is tell my friend, I'm looking for this subgroup. Okay? Then my friend can look into the population and find the people in this subgroup and actually find out what is Y0 bar and Y1 bar for the population. Right? Because he has a population. You know, I just tell him, can you look into your population? All people with A2 bigger than 0.1. Can you look into there and tell me the average Y for the people in that group that are given the placebo and the average of the people given the treatment? Okay? And the friend said, okay, I'll calculate it. And he said the answer is not, so what we had here was 3 minus 2, right? 3 minus 2, that's what the data shows, right? So we estimate this to be 1, right? Then my friend says, it's not 1, it's 1.1. Okay? Now, if you have that kind of friend, you don't need confidence interval. You don't even need data. Just ask your friend. Or you do need the data to get the subgroup, right? But after you get a subgroup, you ask your friend. Okay? But your friend is a good friend. Your friend doesn't want to make you lazy. The friend will say, it's too easy for you. I'm not going to tell you the truth, even though I know the truth. Okay? So my friend knows the true value, this estimated. He knows the true value is 1.1, but he won't tell me. Okay? Then the next best thing you think, okay, yeah, it's true. You know, if you tell me the truth, then I'm out of a job because as a statistician, I need to do something, right? I mean, I'll just call you on the phone and do nothing. So instead, you ask a friend, can you tell me what is the operating characteristic of my method? I want to know how well my method does. In other words, if I keep doing this for new data, right, I want to know how often I'm right. You don't have to tell me exactly when I'm right, but you just tell me on average how often I'm right. Okay? Then the friend says, okay, that one I can do for you. Then your friend will say, okay, what method did you use to construct this interval? Then they say, oh, it's some free program written by some Professor Loh called Guide. So your friend downloads my software. Okay? And then he replicates what you do, but an infinite number of times because he has the whole population. All right? So now this guy called G-O-D, he has the whole population. So he follows what you did for one trial. He will do multiple trials, okay? Do many, many trials. Every time he does a trial, takes the data, he runs guide, he gets a subgroup. And the subgroup will change. But because he has a population, he knows what is the truth. He knows whether this interval captures the unknown or not. Because he has the population. Can you follow that? You see? So this friend has the whole population. So he can do simulations, right? So he takes one sample, same size as your sample, from the same population that you took, all right? Obviously not your sample, same sample, but very close to the same sample. And he runs guide. He gets this subgroup, and he follows your formula. Now this will change because his sample is different from your sample, and this will change. But he still uses 2.1 because he follows your instruction, right? So he can calculate this interval. It's two numbers, left and right number. But because he has a population, since he knows what is this subgroup in this sample, he puts that population down. He knows whether the difference, the true difference, is actually inside this interval. Because he has the whole population. This subgroup is random, but it's a real subgroup, you know. There are people with these characteristics, right? There are people in the population with this characteristic. So if you have the whole population, you will know what is the true difference between drug and placebo. We don't know because we only have a sample, and so we estimate with this. But if you have the true population, you put the population down, and you can calculate the expected value, the true expected value, right? Okay? So your friend can do this exercise, and he calls you back, and he says, hey, I'm sorry, you know, you wanted 95%, you only get 89%. That means your method here is not really 95%. Good, it's only 89%. What will you do? Suppose you get fired if you don't get 95%. What will you do? You change your alpha to make it wider, right? If somebody tells you, you think you're getting 95? No, you're only getting 89%. Then you change 99% nominal to maybe 96% nominal. Wider, right? So now you change it, and instead of 2.1, you go to 0.020, and this may be 2.2. All right? Now you use 2.2, and you call your friend again. Okay? Can you do it again with 2.2? Then your friend say, well, you really ask a lot. But, well, I have a supercomputer. I can do it very fast. So 5 minutes later, your cell phone rings, and he calls back and says, oh, now you get, previously it was 89%, now you get 91%. Oh, so if I choose 96%, if I choose 95%, I get 89%. If I choose 96%, now I get 92% or 91%, right? Okay. So what's the next step? Change 96% to 97%, right? Keep increasing this until you hit 95%, right? But you know what happens in this story? Your friend doesn't answer the call anymore. He got fed up of you. Okay? So suddenly, he disconnected his phone. So what do? You do what your friend did. You replace the population with the data, and you do the same simulation. That's called a bootstrap. You take your data as a population. You draw observations from this data with replacement. Otherwise, you take back the same data all the time, right? Okay. Because your friend won't answer the phone, right? So you don't have access to the population anymore. But you assume that your data are actually representative of the population. I mean, that's your only hope, right? If your data are not representative of the population, nothing you do will be right, right? So you have to trust your data is representative of the population, and your sample size is big enough, right? Now you put your data in the computer, and you do your own simulation program. Instead of every time drawing from the true population, you draw from this data. But because you draw with replacement, you can draw as many times as you want. All right? Okay? So every time you draw from this data, right, you will get a tree. You will get a subgroup. You can calculate that interval, but you also can calculate what is the true value of x1 bar, x2 bar, because you have the data for the population in there. Okay? So you can do this, and you don't have to pay any cell phone bills because you're not calling anybody until you hit it, 95%. Okay. So another way to think of it is the following. Basically, you can think of this t interval as broken. The t curve was not developed for this kind of complicated process. It was developed for RID normal distributions, right? Okay. If your data are really RID normal, fixed mean, this t curve is perfect. It's not even asymptotic. It's exact final sample, right? But now we are in an imperfect situation. We don't have normal data. We have more crazy kind of situations. But this t curve can still be used. It's like you have a bathroom scale in your house, right? You use it. But you know it's not accurate. Okay? But you know that if your weight today, the bathroom scale shows is higher than yesterday, you know you have gained weight. Even though it's not accurate. If suddenly the scale shows 1 more pound today than yesterday, you know you have gained weight. Right? It's just that you don't know when it says your weight is 150 pounds, whether it's really 150 pounds. That you don't know. But if it says your weight is 151 pounds, you know that your weight is higher than when it showed 150 pounds. You need to calibrate it. You need to calibrate it. You need to be able to say 150 pounds on my scale means 140 pounds real weight. 152 pounds on my scale means 142 pounds real weight. You need to calibrate it. Once you calibrate it, you can use your scale. Once you know it's like foreign exchange, right? $1 US is equal to how many Singapore dollars, right? Once you know the conversion rate, you can still use US dollars, so you can use Singapore dollars. In fact, temperatures, we have Fahrenheit and we have centigrade or Celsius, right? You don't throw away the thermometer just because there's no Fahrenheit reading. You just have to put another tape there. They say that 0 degrees Celsius is 32 degrees Fahrenheit. 100 degrees Celsius is 212 Fahrenheit. And then you interpolate in between, right? Okay? So this is the idea of bootstrap calibration. And it solves the problem. Because this method will get you the right number. So the right number here, in the end, if you want 95% confidence interval, may not be 0.025. This is too short. But you will use new 0.001 maybe. Because you do this simulation, and you say that you find that you have to go up to there to get 95% coverage. Okay, if I have to go up to there, now I go back to my t interval, and I say 0.01 here is 2.5. Now I put 2.5. Okay, so the interesting thing for me was that this idea, I had it in 1987. 30 years ago, I wrote a paper in JASA on bootstrap calibration, nothing to do with subgroup. It's basically trying to calibrate the alpha. Okay? And then I didn't think of using it until a year ago. And suddenly I found that, gee, this can be used, right? So this slide, you can read this basically what I mean by calling the friend. F is the unknown. Is the known distribution. So this is what the curve is, right? So you go back to calling the friend, right? First I try alpha is 0.05, and the friend calls back, oh, your coverage is maybe 0.90. Then I tell my friend, okay, can you reduce alpha? Then your friend calls back and says, oh, it's better. This is a true coverage. And go up to that. Say, oh, too much, right? Too much. So you just pick. You could linearly interpolate, or I just take the last one before it crosses the 95%. This is the actual coverage you want to get for the interval. Okay? So you adjust your alpha, okay, so that your nominal coverage will, you have to make it longer, basically, right? At one time, I thought of making this longer. There are two ways you can make this longer. One way is to change this. One way is to change the standard error, the variance. This is very hard because the variance here may not be the same as the variance here, right? See, this method will give me confidence intervals for every subnode, not just the one you want. Okay. Now, I had thought about getting only for the one you want. But how do you define what you want? How do you define what you want? I mean, if you know nothing about the data, I get two subnodes. Which is the subgroup that you want? The left or the right? Okay. So you look at this picture, you may say, oh, I know what I want. Because the left has a bigger separation, right has a bigger separation than the left. Right? So should we always do that? Always choose the one that has bigger separation than the left as the subgroup? So this is a conceptual problem that still I started to think about and I don't know how to solve. What's wrong with this? What's wrong with saying that the subgroup is the one where the difference is larger than the one that there's smaller difference? What's wrong with that? What's wrong is that if you always say that the one that is larger is the subgroup, by virtue of the fact that this difference is larger, your estimated treatment effect is biased. Because you always choose a bigger one. Right? You always choose a bigger one. So you see, for every subgroup, you can estimate this value, y1 bar minus y0 bar, right? If you always choose the one where this is big, then you have a bias in your estimate. On average, it will be higher than the truth. And this is disastrous if you're making a drug. Because then you see that, oh, this difference is 2 or 1 unit. Oh, that's fantastic. But maybe the truth is not 1, but 0.5. You know? This is something I still don't know how to solve. This may be easier to solve, but let me give you another example to illustrate to you what is the difficulty. Suppose I grow the tree. I get 3 nodes. I get 3 nodes, not 2. Okay? Then which is the subgroup? Right? So instead of 2, I get 3. And there's one that is even bigger than this. Do you always chase after the bigger one? That's where the bias comes in, right? Suppose I get 5 nodes. Then you always choose the one that's biggest. You're going to get bias. Right? I don't know how to solve this problem. I think the doctors or the biologists must know what is a subgroup that they want, not let the data point to the subgroup. Right? But if that's the case, then how do you do any kind of studies, simulation experiments to incorporate that fact? Right? You see, so my point is the following. Suppose I have 3. Right? So in here, there's no separation. Okay? In here, there is some separation. All right? In here, there's even more separation. All right? So which is the subgroup? You say, oh, this is more. But it could be by chance, this is slightly more than this, just by chance. So the true subgroup may be this one, but just by chance, this is a little bit less than that. You choose this one, your separation is too much. Your estimated separation is too much. So overall, you get a bias estimate. Right. I have some simulations to show you that the confidence interval method actually is pretty good. See? So before that, let's look at this. Right. So I did a simulation just to get the coverage, get the confidence intervals. And you see, I have the drug A and drug B. This is a diabetes example. This is naive. Right? I just use the T method, no correction. I want 95%, but with sample size 100, I only get 91.7% for drug A, 92% for drug B. But once I put a bootstrap and change that, I'm going from 917 to 930, 920 to 947. Overall, on average, it's about 94% coverage. Now, my sample size increases to 1,000. See, I'm reaching 95% exactly right. Okay? So as far as the interval is concerned, it's okay. Right? But the center is biased. So the y1 bar minus y0 bar is biased. So the interval is like this, right? y1 bar minus y0 bar plus minus some t nu alpha over 2. So I put an alpha star. That's the calibrated alpha, right? SP square root 1 over n1. Okay. The trouble is the expected value of y1 bar minus y0 bar, right? Is not equal to mu1 minus mu2, mu0. That's bias, because I always choose the bigger one. So what happens is that, so imagine this is mu1 minus mu0. This is what I want to estimate. Okay? My estimate is always biased, so my estimate is always high. Always tends to be on one side. To get the right coverage, I need to change this more than I really need if this was unbiased. So it was, if this is unbiased, if this is here, then I just need some, if it's close to here, that's in a short interval. But because it's biased, I need to have a much wider interval to contain this. Right? So the problem one problem that's left to be solved is how can you debias this before you do the calibration? Somehow shift this closer to this, then get the interval around it. Not let it stick on one side and then get it. Because in order for this interval to cover this, because it's so far away, your interval has to be wide. Much wider than if this point is closer here, right? Okay? Yeah, I have some other things. Okay, maybe I'll end with this. People always tend to ask, how do you know you got the right subgroup? Okay. My answer now is that you never know whether you get the right subgroup because the subgroups are not unique. So here's an example. In this example, I have a biomarker, goes from 0 to 10. And this is the mean, right? So I want the difference between, so here is the mean for placebo. So placebo doesn't do anything. But the drug has an interaction with the biomarker level. So the higher the biomarker, the better the drug mean, right? So if you say this is your subgroup, the subgroup is if the biomarker is bigger than 5, all right, then the difference between the drug and the placebo is about this minus this, right? But if you make it, if you think there's not big enough a difference, you can shift your cut to here at 8. Right? Then the difference is this over here minus this. So now you have a much bigger effect. But your subgroup is smaller. So if you're a drug company, even though this can get your drug approved, you may not want it because you don't sell to many people. Because your subgroup is so small. Only 5% of the population. Right? So then you may want to push it down so that you can sell to more patients. But when you push it down, your difference between the red and the black line will be smaller. Right? Now, if this is the case, what is the true subgroup? It's smooth. It's a continuous curve. There's no true subgroup. It's not a jump. Right? It's not a jump. So, in some sense, it doesn't make sense to ask, what's the chance that your method will find the true subgroup? Because what is the true subgroup? Right? So, and remember last time when we first talked about the breast cancer data? We mentioned about estrogen receptor status. Do you still remember? No, the guy found the progesterone receptor status as the split. The Cox model said that the progesterone receptor status is significant, but estrogen receptor status is not significant, right? Okay, now, the last few minutes, I'm going to revisit this. I take out progesterone receptor status, exclude it from the data. I run it again. I get this. Now it's splitting on estrogen receptor status. So I get about similar kind of things. On one side, no difference. On the other side, there's separation. All right? Now I show you both. This is with progesterone receptor status, the original one, which will be this subgroup. And if I don't use progesterone receptors, I get this bigger than 8. I get this 9 or more, right? I get this subgroup. Right? So which is the true subgroup? Is it the intersection of both? Is it the union of both? Right? This part is this region. This part above the blue line is this region. Right? These two pictures tell us that as long as you're inside here, the effect of the treatment is better than average. If you look at the intersection, the effect is even higher. If you take a union, the effect will be a bit lower. Right? So now, which is the true subgroup? You can have 2 variables, 3 variables defining the subgroup. And they are all subgroups because there's no unique answer. Right? If you're a drug company, you want to sell the drug to as many people as possible, you take a union. And then you do a clinical trial with everybody whose progesterone receptor status is bigger than 21 or whose estrogen receptor status is bigger than 8. Okay, and now you do a clinical trial. But if you're worried that if you do that, the treatment effect is not big enough for FDA approval, then you will take the intersection, right? Both this condition and that condition. And then you're more guaranteed that your treatment effect will be higher. But then your patient population is smaller. Right? But the point here is there's no true subgroup. There may be yet another variable that was not collected, right? That will intersect with this 2-dimensional space. Okay, right? So, so this is what I learned working on this. It's a very interesting problem. There are a lot of conceptual things to think about, including just definition of subgroup. You know, I'm doing subgroup identification. What are you identifying? What is the subgroup you're identifying? You know, you just identify something where the treatment effect is enhanced, right? No hope saying that, oh, this method is better because this method has a 90% chance of identifying the right subgroup. In order to do that, you have to say what is the right subgroup. Then, you know, and that may not exist in whatever problem you're studying. Okay, so anyway, I think I promised you to stop at 4:45, so I think I better stop now before everybody complains. So everything I said actually are all these references, and you're welcome to read them if you're interested in details. There's no way I can give you all the details in a finite number of hours. And if you want to try, If you want to try some of these examples, like the breast cancer example, they are in the manual. That example is in the manual. The data are up there on the web, so you can try all these things. And the manual will tell you exactly what to do to run, to reproduce some of these pictures. Okay, well, thank you very much.